Welcome back. We're in momentum on worksheet number 2, problem number 5. A low friction lab cart, meaning kind of frictionless there, has a mass of 1 kilogram, is at rest, and has a spring plunger compressed and locked into place. 24 joules of elastic potential energy is stored in the compressed spring. A second similar cart of mass 3 kilograms is brought up next to the first cart. Trigger is released and the two carts are pushed apart. I'm going to determine the final velocities of both carts. Okay, cool. Sweet. So we look at that and we go, okay, what's the action here? Trigger is released and both carts are pushed apart. So I don't know, trigger released and pushed apart. The pushed apart was probably the one that we actually care about. And so there's my action there. So let's go ahead and draw two different states here. So we first had a cart and we had some sort of plunger. If you remember, like when we used these carts before, I showed you that there was like this annoying plunger that was on here, and that was like spring loaded, and there's like these buttons on top that you could make it, spring out slash lock into place. This is the plunger that we're talking about. So we have one cart with that spring compressed up there, and then like right next to it, we have another cart with no spring in it. And if I go and I release that by pushing that little button on top, it's going to come in contact with this guy and they're going to push one another apart. You might say that the first one here, let's call this cart A and this cart B, that cart A is going to push cart B away. Great. But then Newton's third law, I also know that if cart A pushes B, cart B is going to be pushing A. Okay, cool. So then afterwards, as you kind of expect, B is going to probably be moving to the right-hand side, and A is then probably going to be moving to the left-hand side. Let's go draw that. So then afterwards, this guy is cart A here, and he's going to be moving this direction. Maybe I should label that A up here a little bit more. That's going to be going that way, and we don't know how fast. And it's got some like plunger then that's extended out. And this guy over here is going to be object B, and it's going to have some other, we'll call that VB velocity, call that VA velocity. We don't know what that is either, but it's going to be going away. At the beginning here, we know that both of these things are going to have a velocity of 0, but we have some energy that's stored in there. Well, let's go ahead and do a LOL diagram. Why not? That might be helpful. So I'll do LOL diagram, and we'll put our system in here. What do we want to make our system? I'd make it both cart A and cart B. Why not? You could do it with energy transferred in and out, either way that you want. And so then I know that we have kinetic energy. We don't have any of that. Gravitational potential energy. Oh, I don't have any of that, and I know that the gravitational potential energy is going to be 0 because let's just go ahead and define that this to be the UG is equal to 0 line. That makes sense. But elastic energy. Well, we got a bunch of that. I don't know, 5. And then afterwards, I know that I don't have a bunch of that because the spring's already back to its natural state. And so then where did this energy go? Well, it went into kinetic energy. Did it all go into kinetic energy? I don't know. Maybe some of it went into kinetic energy, and maybe some of it went into thermal energy. We got the springs decompressing here. We also have two objects that are like pressing against one another and hitting one another. That's like a collision with the skate park demo. So is there thermal energy in this one or not? I don't know. Maybe I'll put it like this with like a little question mark there. And if I figure out that there's no thermal energy transfer, meaning that like all the energy goes into kinetic energy, well then I'll just go back and revise this. In reality, it's going to be something like this. And if we need to make approximations, we'll go back and do that. Okay, so we got an overall idea of what's happening with energy, what's happening with momentum. Well, doesn't it look like we're going to be creating momentum here? We have two things that aren't moving, and then now we have two things that are moving. Isn't that creating motion? Well, let's think about it. We know that momentum is a vector as well. It's got a direction to it. So this one's going to have some momentum going that way afterwards. Well, and this one's going to have some momentum going this way afterwards. Well, if momentum has direction in it, this guy is going to be negative, right? And this one's going to be positive. Now when I add these two things together, I could get 0. right? If this one is just as positive as that one is negative, it would add up to be 0. And over here, I see that at the beginning here, I didn't have any momentum. And if I add that to the beginning over here, I didn't have any momentum either, and I know that that would for sure be equal. I know that to be true, and this might be true. Now, if I go ahead and let's define our system for momentum here, because I'm thinking about with momentum as well, we'll make it both cart A and B as we did with energy there. And if that's true, then we know that the change of momentum must be equal to 0, because we have everything that's interacting, everything that's has motion and will have motion is interacting there. Is in the system, sorry. We know that the momentum beforehand is equal to the momentum afterwards. And wait, that's what I just said here. That's what we just set up here. We said, hey, the momentum beforehand, it just happened to be 0 in this case, and so then the momentum afterwards must be the exact same amount, which happens to be 0 in this case. And this is how we know that it can be true. Okay, cool. So regardless of whether there's thermal energy or not, I know every time that there is no creation or destruction of momentum. And the nice thing about momentum is there's no other forms of momentum like there is in energy. There's all these different forms of energy, and maybe the elastic potential energy goes into thermal and kinetic energy. I don't know, it's a little bit complex. But in momentum, it's much more straightforward. There's just momentum, that's it. And so I know that this to be true. And as we just said, but I'll go ahead and write it out, the momentum of A beforehand plus the momentum of B beforehand is going to be equal to the momentum of A afterwards plus the momentum of B afterwards. And we already said that this bit is 0 and that bit is 0 because they both have a velocity of 0 at the beginning. Okay, meaning that 0 is going to be equal to the momentum of A plus the momentum of B. I could go ahead and rearrange that, and we know that A is going to be going to the left-hand side, so let me move A over there. So negative the momentum of A is going to be equal to the momentum of B. I just subtracted the momentum of A over to the other side. Oh, okay, cool. Well, what is this? Well, I don't know. Let's put in what we do and don't know. I know that this is going to be the mass of A times the velocity of A, whatever that is, and that's going to be equal to the mass of B times the velocity of B. Okay, great. Do I know these things? Let's go look back up. And here, low friction lab cart, we have some sort of mass here, and the mass of both of these things is, oh gosh, is not the same. This one is A, and this guy is the mass of B here. Oh, okay, great. And we don't have any of the velocities. Okay, great. So then I don't know either of these velocities. So let me go make a ratio here. So I'll get the let me get the mass over on one side and the velocity over on one side. Why would I do that? Well, I'm looking at this and going, well, I know these masses over here, so I'll put them on one side so I have all the knowns here, and then I'll have the unknowns over here. Maybe that'll be helpful. I don't know. Because right now I can get a ratio of those velocities there. Hey, check that out. The mass of A was 1 and the mass of B was 3. And so I know the ratio of their velocities. Cool. Which is nice. Because if I knew that the velocity of B was 1 meter per second, then I know the velocity of that A is going to be, has to be 3 meters per second. Cool. So that's this is actually really, really useful. So I kind of, let me put a box around that so I don't forget how useful that is. I know that I haven't solved it yet. So then how do I actually go and solve it? Well, it seems like I can't do that with just momentum because there's nothing else we could do. There's no other momenta that we can look at or analyze. So let's go look at some other information. It says that 24 joules of elastic potential energy is stored in that compressed spring. Okay, so then, all right, so now we'll check that out. We have elastic potential energy is going to kinetic energy there. And we have to use that. Now, do we know how much is going to thermal energy? No, it doesn't tell us anything about that. Can we figure out how much is going to thermal energy from momentum? It seems like not. Momentum and energy are two separate things. Now, it does say that it is a low-friction lab cart, and maybe we're reading that this is frictionless then. And maybe we're not worried. Maybe it's not colliding. Maybe they're like already touching at the beginning, so there's no extra collision like in the skate park one. So let's go see if we can do this without thermal energy first. And maybe we can get a little bit further. And if then after doing that, we have a better idea of what's going on, maybe we can go back and put in thermal energy if we could even calculate that in the first place. Okay, cool. So let's try it out. So then in this case, I know that the kinetic energy afterwards is going to be equal to the elastic potential energy beforehand. Okay. EL beforehand. So we know that this is 24 joules of elastic potential energy beforehand. And so afterwards, well, I just have the kinetic energy of both of these things. Oh, I'm going to run out of space. I'm going to do this on the other side because I have a little bit more room over here. Like that. And I'm going to make a little divider here so I don't mix up my momentum and energy calculations here. So the kinetic energy, well, I know it's the kinetic energy of A, and it's going to be the kinetic energy of B. Cool. What's the kinetic energy of A? Well, it's just 1/2 the mass of A times the velocity of A squared, plus the kinetic energy of B, the mass of B, times the velocity of B squared, and that's going to be equal to 24 joules. Okay, cool. Let's think. Do we know the masses? Yeah, we know the masses. Do we know the velocities? I don't know the velocities. Well, let's go ahead and let's put them in, because I do know something about the velocities. Actually, I have this ratio down here. And even though it's, you might say, oh, we derived that from momentum. Well, it's a ratio of their velocities there, period. And I'd have the velocities over here as well. So let's put in, I'm going to multiply both sides by 2 there to get rid of that 1/2. And I'll put in the masses of these things. The mass of A was 1, so I have 1 times VA squared, plus the mass of B was 3 times VB squared, and then I multiply both sides by 2 to get 48 joules over here. And let me go drop the unit here just for clarity's sake. So now, well, I could use this ratio here, and I could get rid of one of these variables, because if I go and rewrite this a little bit differently here, maybe I'll write 1/3, oh gosh, we have negative 1/3 VA is equal to VB. Well, now I could go and I could put that in for, VB, let's say, and then I'd have just an equation in terms of VA. So let's go do that. So I'm going to take this guy and I'm going to put it in for there. And let's see what happens. So I have VA squared plus 3 times negative 1/3 VB, and then the whole thing is squared, right? Because the VB is squared, and now my VB is this whole thing, so that's why I got to put in parentheses there. That's going to be equal to 48. I got to distribute that there, so it's going to be now positive, because negative 1 times negative 1 is positive. And then 1 squared is 1, 3 squared is 9, so I have the original 3 here, now multiplied by 1/9 VB squared, plus, oh, sorry, not VB, oh gosh. Both of these, oh no, there we go, there we go. Both of these, that's not a VB either, that's the VA from down there, because I just substituted that in, sorry about that. So now, and we have the VA over here, still squared, is equal to 48. So now I can just simplify this a little bit more. 3/9, that gives me a 3 down there and just a 1 up there. So it's just 1/3 that. So that means I have 1/3 VA squared plus 1 VA squared. Well, that just gives me 4/3 VA squared. 4/3 VA squared is now equal to 48. And so now I can just solve for VA. Grab my calculator, 48 times 3. I should be able to do that as 144. That's a gross. Then divide it by 4, and then take the square root of that, which is just 6. So VA is 6, and I'll go put the unit on this meters per second there. Now, if VA is 6, I divide, well, now it's just, 1/3 of that is now going to be VB, so I know it's going to be 2 there, because I'm just taking 6 and divided by 3 there. So now I also know that VB, well, you could also just put it down in here, VB is going to be 2 meters per second. Shook. And I can go ahead and put that in. Well, if I put it in for here, I know that it's going to work over here because that's where it came from. And I know it's going to work from here because that's literally where it came from. I pressed stop and then I immediately recognized that one of these has to be negative because we said one of them is going to be moving the opposite direction. And I didn't do my classic, let's go back up and make sure this makes sense. We said that VA is going to be going to the left, VB is going to be going to the right, so VB is going to be the positive, VA is going to be the negative. where did the negative come from? Or when you put it into this equation or this equation over here, there's that negative bit there, which I just didn't carry over in my mind. Furthermore, notice that where does it come mathematically, though? When I go and I do this, I got to take the square root of both sides. And remember, whenever you take the square root of both sides, it's both the positive and the negative solution. And sometimes one of them is extraneous, or erroneous for that matter. And you might have to throw that out. And when we combine it with momentum there and what we already know to be true, the velocity isn't both going positive and negative. It's just one of them. So it's negative for this one and positive for that one. Cool. That's it. All right. See ya.